I am pleased to introduce Jennifer Neville, Associate Professor at Purdue University with a joint appointment in the Departments of Computer Science and Statistics. Her research focuses on developing data mining and machine learning techniques for relational and network domains, including citation analysis, fraud detection, and social network analysis. Today, she will present a talk titled, "Are We Too Smart for Our Own Good? How Large-Scale Machine Learning Systems Can Vastly Exceed Human-Level Decision-Making Abilities." Please take a moment to silence all electronic devices and no audio or video recording. Thank you, and enjoy the talk.
Okay, thanks. Welcome to the first talk in the afternoon session here at the Dawn or Doom Symposium. So I'm Jennifer Neville, and I'm going to be talking to you about my research area, which is machine learning and data mining, and how that fits into the broader context of what's being discussed here at the symposium, which is artificial intelligence. So it's really an exciting time right now for machine learning and big data in general, and that's really happened because of a confluence of many events that have come together at the same time. So we really have had unprecedented levels of data collection recently, and so that combined together with large-scale systems that can automatically have the power to search over these large data sets, combined with machine learning methods, we've really been able to have a number of successes that have really transformed how companies and organizations and big educational facilities like Purdue have really transformed how they make decisions based on these methods. So let me give you a little history of the field of AI and machine learning and how that fits into it. So AI started not very long ago, in 1956. It started as a summer project at Dartmouth, started by John McCarthy here, who convinced some of his colleagues, Marvin Minsky and Claude Shannon, to have a workshop. He was then at Dartmouth over the summer to have 10 people come together and discuss how can we turn learning and intelligence in general into something that can be simulated by a machine and an algorithm. And so this really jump-started the area of AI and machine learning, which is a subfield of AI that focuses on this issue of how can we make algorithms and machines learn. And so at the beginning, in the initial research in this direction, what people did was try to take their understanding of how processing happened in the brain and how we as humans learn and turn that into a formal algorithmic process. And so one example is the perceptron, which is the first basic machine learning method, which tried to mimic what they think neurons do in the brain, which is stimulus comes into the neuron and it builds up, and once it reaches some threshold, then some activation happens in the neuron. And excuse me if I totally butchered the neuroscience there, because I'm just an algorithm person, but basically this mathematical model that was developed by Rosenblatt is the first version of that, and a mathematical version which was called a perceptron, and that eventually turned into what you might know of as neural networks and what you might have heard of now in the news as deep learning. so that the search happens in a place where we're likely to find a good model. So in contrast to knowledge-free, where you can just search anywhere across the entire space, now we try to use our own prior knowledge to constrain that space. Okay? And then in the 90s, I guess I should say historically, before the 90s, most of this research was going on in the computer science community. And there was other research going on in statistics in terms of modeling, but these particular kinds of artificial intelligence methods were happening in computer science. And in the 90s, we started to merge more with statistics and take ideas about probability and statistics and incorporate those into our models and our objective functions and our search procedures. And that's sort of reflective of the fact that now here at Purdue, I have a joint appointment between computer science and statistics, because now there's a lot of common overlap between the two areas working on these methods. And so that reflected, I guess, from when I started in machine learning through today. Things are very statistical at this point. And the major idea that's come since then is the focus on, instead of learning one model, to learn a set of models, which we call ensembles. So we now focus on mixture models or ensemble models, where instead of just learning one thing, we learn many, many different kinds of models and combine them together. And that's produced even better results. Okay, so to give you a couple example applications of how this plays out in the real world, because that was very abstract up until this point, one famous example of an application of machine learning was from the 90s, where Usama Fayyad and some other colleagues of his focused on analyzing data that was recorded at Caltech in the second Palomar Observatory Sky Study. So they had telescopes scanning the sky, and they were taking images of everything out there in the universe, and they had a method of identifying parts in the images that were likely to be stellar objects. So they actually had 100 million examples of things that were potentially of interest to astronomers. But they couldn't manually go through and consider each of those 100 million things to study in more detail. And so what they wanted to do was to have a machine learning method that could take some examples of things that were good to look at versus not good to look at, and learn how to automatically categorize all those examples so the astronomers could focus their attention on the things that were likely to be of more interest. And so what they had was 3 terabytes of data. So if you've heard a lot about this big data rage going on right now, a lot of us in the community say, well, you know, we were looking at big data in the 90s, right? It's great you guys all caught up with us, but we've been doing this for a while. And so they were able to learn a model with only 1,700 labeled examples. They had 40 features for each of the images, and they categorized them into things like star, galaxy, nothing, and I think some other kind of category that's related to stars. And they were able to get model performance where they were able to predict on the rest of that 100 million with 94% accuracy. And more importantly, they were able to successfully, the algorithm was able to successfully categorize things that were too faint for humans to even detect in the image. So the humans looking at it couldn't categorize it, but the algorithm was able to. Okay? So this is an example of the algorithm augmenting human performance. Right? So what we wanted to do was not automatically categorize these stellar objects and then go off and do something without consulting the humans. The point of these classifications was to target human effort on the things that were most likely to be fruitful. Okay? So another example of that is work that I myself have done on detecting stockbroker fraud with the National Association of Securities Dealers, who are now known as FINRA. So part of their mission is to monitor possible fraud and malfeasance among 600,000 stockbrokers that are registered to trade on the NASDAQ stock exchange. And so they have the resources to investigate about 6,000 brokers every year, and they want to target those investigations on the brokers that are most likely to be involved in fraud. And so they've constructed handcrafted rules over time to try to figure out which of those 600,000 brokers are the places that they should focus their effort. But they were also interested to have machine learning methods, or to see whether machine learning methods could help them better target those resources. And particularly, they were interested in having methods that were able to exploit the social, professional, and organizational networks among the brokers as they worked together, because it was thought that fraud was spread through their social networks. And so I worked on new methods to try to be able to use that new type of data in a principled way in the models to be able to predict which brokers were likely to be involved in fraud. And the results were that the models significantly improved on what the current methods were that NASD was using. And most importantly, they were able to find brokers that wouldn't have been caught by their current, at the time, handcrafted rules. So the methods were able to go significantly beyond the things that they even knew about the data and find new kinds of examples that they were interested in looking at. Another example is in recommender systems. So these are things that you probably interact with and don't know it every day. So if you've ever been on Amazon where they've suggested you might be interested in a particular product based on what you just bought, they're using a recommender system that uses a general algorithm, general method called collaborative filtering, where they try to decide based on past purchases of all the other customers that they have, which things are you going to be likely to buy after you've just bought something. So they use your purchases to identify similar customers to you in their space and figure out new things that they could recommend to you. And the importance of using machine learning methods for these kinds of online systems is so extreme that Netflix, who also do the same thing by trying to suggest to you movies based on what you've watched or what you've rated, they, in 2006, set up a competition, an open competition, to get machine learning researchers to help improve their algorithms for doing this collaborative filtering. So specifically, they offered a $1 million prize to any algorithm that would be able to reduce the error on their predictions by 10%. Let me say that again. All they wanted to do was reduce their error by 10%, and they were willing to pay $1 million to get that to happen. And so, and this is to predict for a particular movie on a particular user with a particular movie, what are they likely to rate that movie as? So they can do a better recommendation for people, because obviously they're going to recommend to you movies that you haven't watched that you're likely to rate highly, okay? So this produced a huge amount of research in the machine learning community as many, many groups of people tried to solve this problem. It was fueled by the fact that Netflix released 100 million ratings that they had from 500,000 users for 18,000 movies. And that was the training data. So you could use that to train your algorithms, and then you would upload the algorithms to the system, and they would apply it to new data and tell you how you did on their evaluation. And so 2 teams in the end exceeded this 10% threshold, and since they were tied, the person who had submitted the results fastest won the prize. And so this is a team that's primarily from AT&T Labs Research in New Jersey, and they have at least 3 papers on the algorithms that they used to win this competition. But the main thing I wanted to tell you is that their approach to win consisted of an ensemble of more than 100 models. So essentially what they did is they took almost all the methods that we have developed and put them all into this problem. And then all of those combined together, they could reduce the error by 10%. But only just, you see, just below 10%, right? So even with all that engineering, we still can get a huge improvement in the predictive error that they had with their methods. Okay, so the current advances, as I said before, in these kind of systems and their applicability and their use in widespread situations has really been fueled by not just the research in machine learning, but the advances that have happened in other areas of computer science and psychology and mathematics. So to just give you a sense of how other research impacts how we can do with this framework, work in cognitive science and psychology focusing on decision-making under uncertainty and new kinds of representations for knowledge, this has really fueled our ability to understand what is a good model and how is that going to reflect the kinds of decisions that we want to learn how to make. We have work going on in database, in the area of databases, on data collection, data storage, data management, that gives us the ability to collect all this huge amounts of data that we have and use that to improve our models by having more larger and more variety of the kinds of data that we can exploit. Also, clearly, there's work going on in new kinds of sensors that can collect new data as well for us at a level that we didn't previously have. Clearly, work in statistics and applied math informs a lot of this work because, in particular, it helps us understand how to formulate objective functions and know how we can affect it, what we can optimize and what we can't optimize, and what's effective in terms of use in the algorithms and the models. And then finally, in computer science, also the theory of algorithms, developing faster kinds of algorithms and understanding what are the limits of those algorithms, and also new parallel and distributed computing systems have really allowed us to create larger scale machine learning systems that consider larger and larger spaces of data and models. And so those combinations together have really fueled what we can do. So really, this is only the tip of the iceberg. It's really an exciting time to be in this field because really you're just starting to see the level at which this is going to transform our lives. So a couple of examples of how this will transform things. I think that James Barrett will give a lot more examples tonight. Interestingly, he mentioned Google a lot, and I have 2 examples from Google. So clearly, a lot of this is going on at Google. So one example is self-driving cars. This was fueled by actually a DARPA grand challenge a few years back, where they had a challenge for people to develop self-driving cars that could autonomously navigate over a course of 500 miles. I think it was from Las Vegas to somewhere else in the desert. And so that prompted a lot of research at a lot of universities, and I think it was the team from Stanford that won that competition. But that has since been sort of sucked into the Google sphere, and now they have self-driving cars that can operate very well, at least around in the Bay Area. So one interesting part where machine learning comes into this is that machine learning is being used not to figure out how to drive the car, although it may be used for that too, but actually to figure out models of how other drivers operate on the road so that the car can decide what to do in the context of what other people will decide to do. So instead of coming up with a complicated model that's hand-coded that describes how we all drive, what they want to do is actually learn from watching videos of people drive what are the norms and the rules and the conventions of driving. So as an example, you could learn that cars stop at a line on the ground when they see a red light. When it turns green, they go, but it's the first car that goes first, and the second car waits for that car. When cars come to a stop sign, there's a convention about who goes first if they all get there at the same time, but otherwise, whoever gets there first goes first. Example for things like that are examples. So they're using machine learning to decide how to do that. I guess let me go back a second. I should say that in this case, while these cars can drive really well around the Bay Area, you cannot pick these cars up and take them to Boston and have them work in Boston, because they're based on a lot of knowledge about how the road systems and the conventions of driving happen around in the Bay Area based on the information they have from Google Maps and other things that they're building up at Google. So again, the performance of the system depends a lot on prior knowledge that's encoded into the system. So it's going to still be very difficult to pick these up and have them operate in Boston, or more importantly, have them operate in England, where all of a sudden people are driving on the other side of the road, right? Okay, so the next one is this example of using learning to automate smart buildings and homes. So Nest is a company that has developed thermostats for you to have in your home that uses machine learning to figure out how to simultaneously learn your preferences, optimize the behavior of the system to your preferences. So it's going to learn how hot you like it during the day, how cold you like it at night. It's going to learn your patterns of behavior in your family based on listening to the environment and the amount of light that it senses. It's going to learn that you go to school at 8 o'clock in the morning and you come home at 5:30, but only, 5 days a week or something like that. And it's going to figure out how to optimize an energy consumption given your pattern of behavior and your preferences. Okay? And so this is a startup that then was acquired by Google. So it is now a Google example as well. So this is really only the beginning. There's lots of smart infrastructure now for offices and buildings. But using learning to intelligently adapt those systems is going to be the wave of the future. And finally, as a last example, we are going to start to see personalized medicine coming out of machine learning and data collection efforts. So right now, if you get sick, they decide how to target your drug treatment or other kind of therapeutic treatment, probably based on some gross categorization of you, based on maybe how sick you are, how old you are, maybe your gender, maybe your ethnicity. Okay? And they do that based on some gross statistics about survival rates or whatever of people in that category. Well, we're really coming to a situation where we can target those treatments and personalize them directly to you instead of taking this large category of people and lumping them all together. And how are we going to do that? Well, we're going to combine together specific genome information for each person based on sequencing your DNA. And then we're going to combine that together with some very low-level, maybe sensor-level information about you and how you react in real time to a particular treatment. So down here, this shows you a new form of sensor that can be tattooed on your body and record a lot of different things in a very unintrusive way. Right? So it might be able to measure heart rate, blood pressure, skin temperature, lots of things like that. Okay? And it can stick on your skin and stay there for a couple of weeks while they're monitoring you in terms of how you might react to having a particular drug. And then recording that information over time to see all the illnesses you have and how you're treated and how you respond to that, then you'd be able to learn your own personal way of responding to drugs, and hopefully in the end we'll all be healthier for the result. Okay? So these are all examples where the machine learning methods would hopefully be used for good, right? To improve our lives, to improve sustainability, to improve our health, to make things easier on us, to make us have to work less and party more. Life would be great if that's what would happen. But I guess a lot of the talk in this symposium will be about whether we should be worried about these kind of systems and how they might take over our lives without us really realizing what we're agreeing to at this point in the road. So what I would say to that first is that the success of machine learning algorithms has really been to augment and improve our human decision-making capability. So right now, I think of them as only helping us improve what we're doing. And really one way to think about that would be to tell you about the work in psychology from Tversky and Kahneman. Here's a quote from Daniel Kahneman telling you about how bad we actually are at making decisions. Right? So basically, there's been a lot of work showing that we're actually not very rational. We not only make decisions, snap decisions with very little data, we actually think that we're making a better decision than we are. And so what this means is that if we actually use models that are trained with a sufficient amount of data that we can trust the results of what they're doing in terms of predictions, that can actually help us get away from our own personal biases about how we make decisions in the world. And so this can go from something as simple as your introspection about how your study habits really impact the performance in the classroom, to something as complex as how maybe law enforcement would be targeting particular people when it's trying to protect our safety, right? So there's really a large range of things that if we made better, more informed decisions, we would have our lives improved. However, in this case, when we start to have more and more models that can do this, it's really the data that's going to be driving the decisions that we're making. And so I think an important area for discussion is data policies of how we're going to collect and use and reconsider data about ourselves. So if particular algorithms are making decisions, for example, that you should not be given a loan because you don't have a good credit history and you have too much debt right now, well, you should be able to challenge the decision of those models in case that data that they're using to make that prediction is wrong in some way, right? We can't always guarantee that the data people have is 100% correct. It might be old, it might be stale, it might be maliciously changed, it might be just noisily changed based on some error in the system. And so we should have a way to be able to challenge those results and ask to see what are the data that you think belong to me that you made that decision about. And so more discussions on this level is going to be important as we move forward. The other issue, as things become more and more automated and embedded into our lives, that we have to realize that those decisions are going to give power to the people that the decisions benefit. And so that means we have more and more likelihood that some hacker that goes into the system to try to change the algorithm or change the data to make the decisions go more in their favor than in someone else's, that we really have more and more likelihood that that will happen. And so it's really important that we focus on issues of data, how to keep the data safe, and how to keep the systems secure so that we can counter that problem. Okay, so finally, what I would say in response to this idea that we might achieve human level or surpass human level intelligence without even really realizing it is that I would say that intelligence is much more than learning. So the success that we've had right now with our machine learning systems is because we've really narrowed the scope of what we considered. Okay, so we might have a very large system that decides how to, for your query in Google, what documents should be returned to you as most relevant to that query. That might be a really large system that's really complex, but it's only trying to do that one thing, right? So we don't have a system that can drive a car and learn how to read and learn how to return search queries and learn how to give you medicine if you're sick, right? And so to get to that level of global system, we'd have to be able to engineer a lot of our own prior knowledge into the system, because that is really what's made our machine learning methods work. So when our tabula rasa methods worked terribly, and so it was only as we started including more of our own personal knowledge about the world and how it works into the algorithms in terms of picking the model representation, designing new ones, engineering good features, and picking an objective function that searches over that space of models really well, that's how we got to systems that can learn well. And so bootstrapping beyond that is going to be quite difficult. The area of AI in general has been filled with a lot of hubris for a long time, right? So there have been many times where people have said, oh, this is definitely going to happen, you know, in the next 6 months, in the next 5 years, in the next 10 years. And now we're 60 years later, and still, I mean, we've achieved a lot, but we're still not very close to strong AI, I feel. And so if you think about what has to be put together to have lifelong learning in an intelligent system, we really are going to need to learn how to not just use representations, but we're going to have to learn how to generate those representations, and we're going to have to learn how to put common sense knowledge into our system and learn that over time, and not just make one decision, but plan how to make many sequential decisions over time, dealing with many agents that will be interacting with us in the world. And then, more importantly, we're going to need how to optimize over many conflicting objectives, not just one objective function, but we're going to be simultaneously trying to optimize many things at the same time. And at that time, not just maximizing it for ourselves, but taking into account social norms so that I don't just maximize how much money I will make at the expense of all of you out there. Okay? So, to conclude, what I would just say is that because this is an exciting time, we've had a lot of success that has fueled a lot of excitement and a lot of money for research in these areas, really we should think about how interdisciplinary research between not just computer scientists and engineers, but computer scientists, engineers, and social scientists, and scholars from humanities, and lots of various fields, how we're going to put those all together to start to develop not only the systems that will solve these problems, but the policies and the understanding of the systems so that we can safely use them. So with that, I will stop. Thank you very much. So I'm not at all sure if people are supposed to come and ask questions. If anybody has questions, please let me know. No questions. Okay.
What's the feeling of how much intelligence we have at birth?
I'm sorry, I couldn't hear you. What?
What is the feeling of how much intelligence does a person have at birth? Is there any?
Oh. That's a good question. So the question was, how much intelligence does a person have at birth? I would say that, I guess that's a very philosophical question that I don't generally think about. But I would say we have the tools to start doing this kind of learning. But we don't actually know that much. And it's really through interaction with, our parents and families that tell us how to use those tools that we really start to do this learning.
So we have to accumulate all the experiences of everybody in the whole world to get that level, right?
Well, I would say that we need to better understand what is that basis that happens when we're born, because you might think that we have to just watch everybody and how all the information that they have over time, and then we would be able to achieve this level of intelligence. But if we don't understand the mechanisms that are there when somebody is born in terms of what are the tools that they can use to start formulating representations and figuring out how to associate knowledge with particular decisions, then we still won't get anywhere. So that's really an indication that we still need to go a lot further in understanding that aspect of it. Yeah. Yeah.
Oh, there we go. All right. So earlier you said that intelligence was not the same thing as machine learning, which I think is pretty clear. But I guess you didn't really define intelligence ever. So is there a formula for actual intelligence?
Yeah, so I didn't have enough time to get into that aspect of it, but in the field of AI, people don't even really agree on what intelligence is. So some people would say intelligence is acting rationally, and some people say that intelligence is acting like humans act, which is clearly not rational in some cases. And so I think that there is some disagreement on that, and that is why the AI community has really two different areas. One that's called people interested in strong AI, which is try to achieve human-level intelligence. And then there is an area which I personally feel like I'm part of, which is called weak AI, where we just want to develop systems that will help humans and augment human ability because we are not rational. And so if we had rational decision-making systems, they would help us improve our level of decision-making. But another kind of definition would be the set of things that I listed at the end, that intelligence is not just figuring out how to learn, but it's figuring out how to plan and operate and behave in a complex environment where you're maximizing simultaneously many objectives over a long period of time without direct feedback at every step of the way. So, sure. Any other questions? Okay, thank you very much.